Everybody, it's Ripley back again. Today we're going to talk about the absolute convergence, which is a trip, and then we've got the ratio and the root tests, which are freaking amazing. Okay, so here's what I'm going to do. Let's talk about the absolute convergence test. All right, it's an actual test. If I take the limit as n goes from 0 to infinity or whatever, right? This thing can start at 17 if we wanted to. It doesn't matter. And I take, if I'm looking at the absolute value of any sequence, all right? Now, what I want to show to you, and it's pretty intuitive, but it can be really confusing, all right? If this converges, this implies that this a sub n converges absolutely. So it's kind of like absolutely. It's kind of like a stronger form of convergence. For example, now you may say, well, Ripley, wait, why would I want to do that? Well, for example, let's do as n goes from 0 to infinity of -1 to the n over n squared. Hopefully you agree that the absolute value, if I take n 0 to infinity of the absolute value of -1 to the n over n squared, the absolute value of that is equal to n 0 to infinity of 1 over n squared, which we know converges. Why does it converge? Because p equals 2 or p is greater than 1. Either one of those is good. That implies that this guy, the original series, -1 to the n over n squared, converges absolutely. Absolutely. Now, absolute convergence is still convergence. So don't freak out if you're like, well, wait, what does that mean to converge absolutely? Is it different? Well, it is different. And the reason that it's different is because you can have a series, for example, -1 to the n over n. Now, we know from the alternating series test, we know that this guy converges by AST. However, if I take the absolute value of this, then what I get is n goes 0 to infinity of just 1 over n, which we know diverges. Which means that this guy right here, let me change colors real quick. This guy, while he converges, this is not absolute convergent. All right, because this guy diverges. Now, you may say, why is that helpful? Well, because sometimes it is way easier to look at a series when it's not flippy-flopping around, going positive, negative, or even positive, positive, negative, 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 positive, something like that. For example, let me show you. For example, let's do this guy. I'm going to do, just for giggles, let's do sine of n as n goes from 0 to infinity, which really means it goes from 1 to infinity, right? Because sine of 0 is 0, over n squared plus 1. Now, this is an innocuous enough looking series, but it's actually pretty tricky because think about what sine does. Sine of 1 is positive. Sine of 2 is negative. Sine of 3 is negative. Sine of 4 is positive. Sine of 5 is positive. So I don't have that alternating series. This is not alternating. I know it alternates signs, but it doesn't do it uniformly. It doesn't do it predictably. So my alternating series test is out. Well, what else am I going to do? Am I going to use the limit comparison test? Well, how is that going to work, right? Because this isn't a rational function. It's not a p-series, although it smells like one, right? So I'm kind of stuck. I don't really have a tool yet that I can work with. I certainly don't want to take the integral of this thing if I can possibly avoid it. It would probably be a parts integral, right? Which would be awful. So we don't want to deal with that. So what we use is absolute convergence. We know that if I look at, so let's go look at, as n goes from 0 to infinity, of the absolute value of sine of n over n squared plus 1. Well, what does that do? It makes everything positive, but sine's special because sine is always between, the absolute value of sine is always between 0 and 1, isn't it? So I know that this guy is always less than or equal to the sum, as n goes from 0 to infinity, of 1 over n squared plus 1. Not n, I think I said n plus 1. I apologize. I know that this is always less than or equal to, as n goes from 0 to infinity, of 1 over n squared. Hey, guess what? This thing converges. Why does it converge? Because p equals 2. Now, if this converges, then that implies that this converges, the absolute value of sine of n over n squared plus 1, also converges. Why? Because the series is always less than or equal to a series, a positive series is always less than or equal to another known positive series that converges. So by comparison test, oh my goodness, we're using all kinds of tests. Let's change colors again. This implies that n goes from 0 to infinity of sine of n over n squared plus 1 must also converge absolutely. Now, when you write absolutely, it implies that you use the absolute convergence test, right? We just say it converges absolutely. Since the absolute value of the sequence, when I turn that into a series converges, then I know that this thing converges absolutely. It's a powerful tool. It's not often used, but when it is used, it's very, very powerful. Now, all right, so we got absolute convergence. You're gonna struggle with absolute convergence. You're gonna want to ask me questions and pin me down on it, which is good. That's exactly what you want. Just remember that all series that converge, are not necessarily absolutely convergent. But if you are absolutely convergent, then you converge. All right? They still converge. You may have a series that converges that is not necessarily absolutely convergent. For example, the alternating series test, -1 to the n over n. It still converges. We can't sell it short. It still converges, but it doesn't converge absolutely, which is a stronger convergence. It really is, because the thing that makes this alternating harmonic converge is the fact that it alternates. But in this case, it doesn't matter. We don't need no stinking alternation. All we got to do, that's a what is it, Treasure of Sierra Madre reference. By the way, if I slap absolute values around this, then I lose that alternation between, or alternating, whatever alternation means, then I still converge, so it doesn't really matter. Okay, now I'm about to give you the keys to the kingdom. I'm going to give you the most powerful test. It's called the ratio test. Ratio test. And the ratio test is super straightforward. The ratio test simply says this. If I take a series, given a series, n goes, let's assume it starts at 0, doesn't really matter, of a sub n. If the limit as n goes to infinity, the absolute value, that absolute value is really, really helpful, of the absolute value of a sub n plus 1 over a sub n. Now, if this thing, and I'm going to set 3 equal signs off of this. Those are supposed to be equal signs. Sorry. All right. If this is, well, I'm not even going to use equal signs. Come back. Sorry, I got a kid. Come back later. I'm gonna do 3 things. Sorry about this. If this guy right here is greater than 1, this implies that a sub n diverges. If it's less than 1, I'm going to make my ones a little better. Sorry, you guys, I had to yell at a kid there. Then the series not only converges, but it does so absolutely, because we slap the absolute values around them. Absolutely. And if it equals 1, then I have frowny face. Then I don't know. It's non-conclusive. Non-conclusive. Use another test. Find another test. Do something else, which is cool, because what it says is the ratio test, while it's extremely powerful and extremely useful, it's not useful all of the time. Now, let's just explore this for just a second. What is this saying? It's saying if I have my a sub n plus 1 and my a sub n, and I'm dividing the previous term into the next term, if this is growing, if it's greater than 1, if it's bigger than 1, then that means we've got a problem. What it means is that these series values are growing in such a way that they're not containable. Remember the whole garden gate thing? The garden gate is not slamming quickly enough. If it's less than 1, then suffice it to say that the terms are decreasing at a quick enough rate that we can pretty much conclude that it's going to converge. And not only is it going to converge, but it's going to converge absolutely. If it equals 1, it's kind of like, well, we can't really tell. Something strange is going on. We need to use another test. I'll give you examples. Let's look at this series. This is a really interesting, this is probably my favorite series. We're going to do e to the n over n factorial. And we'll let n go from 0 to infinity. right? Okay, what does this thing look like? Let's list a few terms. Well, e to the 0 is 1 divided by 0 factorial, which is 1, right? Then this is going to be plus e over 1 factorial, which is 1, plus e squared over 2 factorial, which is 2, plus e cubed over 3 factorial, which is 6, plus e to the 4th over 4 factorial, which is 24, plus e to the 5th over 5 factorial, which is 120, plus dot, dot, dot. Now, it looks like e is going to win this race, right? However, let's check it. Because if you recall from our factorials, man, those things get big really fast. So if this thing is going to converge, remember the very first test that I gave you. If this converges, if convergent, this implies that the limit as n goes to infinity of a sub n must equal 0. If it doesn't equal 0, then it diverges. I can flip that, right? If it equals 0, it doesn't necessarily converge. But if it doesn't equal 0, it has to diverge. So I'm going to prove that this thing converges right now. So here's the way it works. Let's change colors. Here's the way it works. We say by the ratio test. And then we just look at the terms. So we're quoting the ratio test right now. We know that the limit as n goes to infinity, a sub n plus 1. Well, what is this? Remember, this guy right here is a sub n. It's my sequence. This is e to the n plus 1 over n plus 1 factorial divided by e to the n over n factorial. Now, I'm going to do a little bit of algebra here. I'm going to take the limit as n goes to infinity. Now, I'm going to do two things at once here. You may want to, well, actually, I won't do two things at once. What I'm going to do is I'm going to, remember when I divide by fractions, I flip and I multiply. So I'm going to rewrite this as e to the n plus 1 over e to the n times n factorial over n plus 1 factorial. Hopefully you can see how I did that. You see it? I flip it up. This guy goes up here. This guy goes right here. And then I just use commutative properties of multiplication to get this where it needs to be. Now this is equal to the limit as n goes to infinity of, you might want to take this step. This is e to the n times e, right? That's what e to the n plus 1 is. Divided by e to the n times n factorial over, that's an n, not a u, sorry about that. What is n plus 1 factorial? Well, we've played with factorials long enough to know that this is n plus 1 times n factorial, right? 8 factorial is 8 times 7 factorial, right? 21 factorial is 21 times 20 factorial. N plus 1 factorial is n plus 1 times n factorial. Now, start crossing stuff off. Goes away, and we end up with the limit as n goes to infinity of absolute value. I don't even have to use absolute values, right? Because I know this is going to be e over n plus 1, which is going to be positive. Well, as n goes to infinity, e is a constant. So guess what? This goes to 0, which is less than 1, which implies that this guy, and then goes from 0 to infinity of e to the n over n factorial, converges. Not only converges, but, whoa, that was supposed to be an A, turned itself into a D, but it converges absolutely, which is awesome, right? That's powerful. Not only did it tell us that it converges, but it also tells me, remember when we first started talking about limits at infinity? It tells me that n factorial puts to shame exponential. Exponential functions grow incredibly fast, unfathomably fast. We can't wrap our brains around how quickly they grow. Factorial functions, it's like, yeah, stupid exponential function, I will crush you. And that's exactly what it does. Because it wins the tug of war, because the limit was 0, which is awesome. All right, ratio test is fantastic. Now, let me give you an example of where it doesn't work. Let's do, how about 2n plus 1 over 3n plus 2? Well, this one's silly. We already know that this diverges, right? Because the limit at infinity, the limit at infinity is 2/3. Let's do cubed. All right, let's do that guy. As n goes from, can I go to 0? I can't. 0 to infinity. Now, we know if I take the limit of this guy, that it's going to be 0 because the degree of the denominator is much greater than the degree of the numerator. Now, this gets pretty interesting, but I need to show you how this works first. Hopefully you're looking at this and you're like, Ripley, I'm going to use the limit comparison test because this guy turns into 2 over 3n squared, right, out at infinity. And then I'll just let a sub n equal 1 over n squared, right? And then I just, by limit comparison test, I take the limit at infinity of this guy divided by this guy, turns into 2/3, which is greater than 0. We have different constants. Remember the limit comparison test, go back and look at your notes. It has to do with values that are greater than 0, rather than 1 seems to be sort of the hinge for the ratio test. So that gets tricky. When you start using a whole bunch of different tests, it can get confusing pretty quickly. However, let's assume that you're just like, oh, I'm kind of a dilettante at this, so I'm going to use the ratio test. So by RT, all right, I'm going to take the limit as n goes to infinity of, here we go, 2 times n plus 1 over 3 times n plus 1 cubed plus 2, and then I take the whole thing and I divide it by 2n plus 1 over 3n cubed plus 2. This turns into the limit as n goes to infinity of the absolute value of, now I'm going to flip this guy over here and this guy up here, and then I'm going to split them up a little bit. This is 2n plus 3, right, 2n plus 2 plus 1, 2n plus 3 over 2n plus 1 times, now this guy goes to the top, so I end up with 3n cubed plus 2, and there's no way I'm multiplying that out. We don't need to. N plus 1 cubed, I'll show you why in just a sec, plus 2. Well, bam. Now, if you look real close, do you agree that if I were to multiply top and bottom out in both cases, I would get a degree equal to 4? Correct? Right? I would get a degree equal to 4, and my leading coefficient would be what? Well, my first term would be 6n to the 4th. My first term down here, if I multiplied this out, I'd get an n cubed. So I'd have 3n cubed times 2n is 6n to the 4th. So I would end up with 6 over 6, right? This is just rational function stuff that we did way back when we started playing with limits at infinity. So hopefully you can tell that my degree of the top and bottom are both 4. My leading coefficients in both cases are 6 over 6. This is equal to 1. Well, 1, according to this, is non-conclusive. Frowny face, do another test. Well, we already talked about which test we would do. We would use limit comparison test. All right, sweet. That's the ratio test. The ratio test, the cool thing about the ratio test is it is the only test that you need to use when we talk about something called power series, which is typically in the next section, depending on which textbook you are using. It's huge. It's extremely powerful. All right? Now, I'm going to give you something called the root test. Now, the root test very, very rarely shows up, but boy, when it shows up, the root test is amazing. And what it does is, think of it as a variation on the theme of the ratio test. It makes your life a lot easier. Whereas, let's say, for example, I add the sum. I'm pulling this one straight out of a textbook I'm using. As n goes from 0 to infinity of, let's go, 2n plus 3 over 3n plus 1. Okay? And I'm going to raise that to the nth power. Raising it to the nth power. And you may say, okay, wait a second, Ripley. Here we go. Let's think about this. Let's see what my Spidey sentence says. If I take the limit of the inside, hopefully you agree that the limit, as n goes to infinity, of 2n plus 3 over 3n plus 1, 3n plus 1 is equal to 2/3. Now, you're probably saying, wait, well, okay, if that goes to 2/3, doesn't that imply that this guy has to diverge because this is not equal to 0? No, you're mixing your tests up because that has an end to it. So really, out at infinity, this guy behaves very much, if I were to go n and n, we know that this term should go to 0. So what we need is a test. Well, the test is called the root test. And it simply says this. If I take the limit, as n goes to infinity, the absolute value of the nth root of a sub n. Now I end up with exactly the same 3 things. I got to quit doing 3 equal signs. I know if this thing is greater than 1, this diverges, which kind of for this reason, because these things start to smell geometric out at infinity. This thing diverges. If it's less than 1, it not only converges, but it converges absolutely. And then if it's equal to 1, new test. It's exactly the same. So let's apply. I'll change colors. Ooh, I haven't used the lovely lavender lately. That's a lot of L's. I'm going to, so I would say by, I guess RT and RT is the same. Let's do root test. I know the limit as n goes to infinity of the nth root of the square root of a sub n, which is this guy, which is 2n plus 3 over 3n plus 1. But this thing is to the nth. Now let's see what happens. Well, the nth root of anything to the n is just that thing, isn't it? Oh, this should be an absolute value too. Sorry. So, man, that's a lot of notation, isn't it? So this is equal to the limit as n goes to infinity. The nth roots and the nth cancel one another out, and I end up with absolute value of 2n plus 3 over 3n plus 1, which is obviously 2/3. Since 2/3 is less than 1, that implies that the limit as n goes from 0 to infinity of 2n plus 3 over 3n plus 1, all to the n. You guessed it, not only converges, but it converges absolutely. It's powerful. It's good stuff. Hey, guess what? You've reached the last of the tests. There are no more tests for convergence. None. This is the last of them. So in the next sections, we're going to talk about something called power series, which are super fun. Functions is power series, and then Taylor polynomials and Taylor series. And then, guess what? We're done. No more calculus 2, which is pretty cool. So thanks for sticking with me thus far. This is the last test for convergence or divergence that you're ever going to have to learn, hopefully. There might be another one in your analysis courses. But yeah, we're kind of done with the hard stuff. Now we got to bring it all together. So think of tests for convergence and divergence as being like techniques of integration. They're real easy to use when you know exactly what you're doing. Right? When you, at the top of your book, it's at the top of the page, it tells you which section you're in. Oh, I'm in ratio test and root test. Chances are I'm going to use one of them. However, when I throw a whole bunch of these at you, sort of shotgun blast them at you on a test, it gets tricky in terms of being able to figure out which test to use and when, very much like using the correct technique of integration was tricky on the integrals test. All right, thank you for your time and attention, and I will see you in class tomorrow. Have a great day.